Good afternoon again. Evan Stamon here for Umaghloko, Making a Difference. Today we're going to look at curve sketching in particular. Although we have looked at all the details of it in previous examples, I would like to look at it as a specific topic on its own because it is very often asked in exams and is a particular type of question to which you can get all the marks quite easily if you obey the rules. So the key thing with curve sketching is we are not drawing it to scale. Okay? We are not drawing it to scale. Okay? Yes, it can't be inaccurate in the sense that it can't be misleading, but the key thing about it is we want to look at the features. And the key features are the x-intercepts, the y-intercept, the stationary points, and if there exists one, the point of inflection. Now, again, we know that for a x-intercept, we need to make y equal to 0. To find a y-intercept, we need to make x equal to 0. We now know that if you're looking for a stationary point, you make the first derivative equal to 0. And what we've seen in a recent video is that to find a point of inflection, you would make the second derivative equal to 0. So I'd like you to really take note of this idea that pretty much every single time that you are trying to find something that is a key feature of a graph, you're making something equal to 0. That is not to be confused with find a point. To find a point, okay, and we talk about any other point on the graph, you need to find an x value and you substitute it in into the f of x function so you can find y, so that you now have x and y. This is very important because very often people forget that because we are so often making something equal to naught, if they're asked to find a point, they automatically make something naught. Be very careful here. If you're looking for a feature, you make something equal to naught. If you're looking for a point, you go and find the particular x value and substitute it in. Okay, so again, please remember that because, for example, okay, if I have f of x, which is the same as y, equals something involving x cubed, I know that because it is y to the power of 1, there will be one y-intercept. That because it is x to the power of 3, that we can get a maximum of 3 x-cuts. And then because of this length of the derivative dropping the power by 1, we can get a maximum of 2 x-cuts, 2 stationary points, two turning points, and we can get a maximum of 1 point of inflection. Now, I'm going to be quite careful here because I have an example later on which shows that we do not automatically get 3 x-intercepts and or automatically get 2 stationary points. Sometimes these things are a little bit fun. So, having done the theory of this, okay, remember we are not drawing to scale, we are looking for its features, and we want to draw it in such a way that it enhances our understanding, not such that we are worrying about plotting points dot to dot. That is what we use computers for. So what I'm going to do now is look at a couple of examples from old exam papers. Okay. This, you can see from the mark allocation that 9.1.1 is not meant to be difficult. Please always keep an eye on mark allocation. How do you find a y-intercept? Okay. You would simply look at the constant value, or you could look at f of naught. But if you did f of naught, you would not be surprised to see that you get an answer of 4. But again, so we're looking for the intercept on the y-axis. This is an old form of asking it. Normally, we would ask for a point, okay, in which case you'd need to answer 0 and 4, okay? But because this one does not ask for a point, your answer of y equals 4 would be sufficient, okay? Calculate the intercepts on the x-axis. Again, looking at 9.1.2, we are experienced enough to know that we are going to simply make 2x cubed minus x squared minus 8x plus 4 equal 0. Again, we could try to use the fancy calculators, or we could try and do something that involves a bit of thinking. Nothing's jumping off the plate at me right now. Yes, it is. So I'm going to let x equal 2. If I let x equal 2, I'm going to get 16 minus 4 minus 16 plus 4 does in fact equal 0. That makes me happy by the remainder and factor theorem. Okay, so as a result, I know that x minus 2 is a factor. And so I know that this therefore, x minus 2 times something, in this case a quadratic, would equal 0. Again, to get the 2x cubed, I need to have a value here of 2x squared. Sorry, wrong color. Let's go back here and grab the red pen. Of 2x squared. I know that to get the value of plus 4 at the end here, okay, I know that therefore I would need to have a minus 2 in here. And again, you can choose which one you'd like to pick. I'm going to pick the minus 8x again. And I know that that is going to come from x's times numbers and a number times x. The outer bracket is giving me minus 2x at the moment, which means that the inner bracket has to give me minus 6x. And minus 2 times what gives me minus 6x. I'm hopefully realizing that this value has to be plus 3x. Okay, I need to go ahead and factorize fully. So x minus 2, 2x, and x minus 2, so plus 2 in this case, and minus 1 equals 0. You check for me if you want to. I've got the 2x squared, I've got the minus 2, the minus x, and the plus 4, excuse me, plus 3x, and I'm happy. So x equals 2, x equals a half, or x equals minus 2. Having found our x-intercepts, what I always think is a good idea is to keep track of these things on our drawing. Again, please note, although this is quite squashed in the bottom corner, I do encourage you to draw it a bit bigger than this, but I'm drawing it for features, not for scale. So again, we know that the y cut is at 4, and we know that the x cuts are going to be at 2 minus 2 and a half. So we can draw them in roughly to scale. So there is 2 minus 2. There is positive 2. There is a half. And we now have a rough idea that because of the fact that this is a positive cubic, it will end up going to top right, which means that it must turn in between 2 and a half. Reading from left to right, it must turn somewhere in between 4 and, so in between minus a half and positive a half and minus 2, and end up going to bottom left. So what we're going to look at now is the idea of finding the coordinates of a turning point. A turning point is found by making the first derivative equal to 0. So what we have here is f dash equals 6x squared minus 2x minus 8 equals 0. So 3x squared minus x minus 4 equals 0. So our factors are x and 1, 3 and 4, and we're going to have positive x and minus 4. So we left our x out here. And as a result, we know that x equals minus 1 or x equals 4/3. Okay, we then need to find y values, so we substitute into the original function. F of minus 1 equals a value of minus 1, so we go in here quickly, it would be minus 2 minus 1 plus 8 plus 4, which in this case is minus 3 plus 12, so it is 9. So we know that this point here, this turning point, will be at minus 1 and 9. Putting in the value of 4/3, again, you can substitute into the original equation. You can use your calculator. I have the fun of doing 4/3 minus 2 times 2 times 4/3 minus 1 times 4/3 plus 2, which is 4/3 minus, will be 2/3. 8/3 minus 1 will be 5/3. And 4/3 plus 2 will be 10/3. And so what I'd have here is 100/27. So 4/3 is paired with 100/27. And again, minus 100/27. There's a minus sign missing here somewhere. There. So cool. We know it's negative. And how did we know it was negative? And it was good that we checked. We could see on the graph that the turning point over here had a negative y value. So again, the algebra must match the graph, and the graph must match the algebra, so please use that to check your work. It needs to make sense. Okay, coincidentally, as we were doing this and filling these values in on our sketch, we've already answered question 9.1.4. What I'm going to strongly suggest you do is to learn to join the turning points with an S shape. Make sure you go through those relevant points, okay, and try and make sure that at the turning points, your graph flattens out. We then need to make sure we go through that X cut, and we need to make sure on our far left here, we go through that X cut, and there we go. Okay, so in this particular example, they haven't asked us for, but more often nowadays they do, is to find the point of inflection. So what I'm going to do is find the second derivative. Okay, and the second derivative here is going to be f double prime, or f equals 12x minus 2 equals 0. Therefore, x equals 1/6. And we can plug it in, and we're going to find out that therefore our y value, hopefully, if I've made a mistake, will equal 2. That does feel correct. Yes, it does. Okay, will equal 2.65. Okay, so we've got 1/6 paired with 2.65. And that will be over here, our point of inflection. Now, again, I would strongly encourage you to make sure that your graph was large enough. I wouldn't make it too large. Okay, well, how big is enough? Okay, I would perhaps try and make it about 10 centimeters by 10 centimeters by 10 centimeters, maybe 15 by 15. Okay, very often they give you axes to draw onto, but make sure it's large enough. But the key to it, okay, are the features. Okay, let's move on to another similar example. Okay, calculate the coordinates of a point where this thing has a local maximum value. Okay, then calculate the x and the y intercepts, and then sketch the function. Again, this is nicely scaffolded. In the good old days, they wouldn't have done this as separate sums. They would have just said 10.2, sketch the function. Okay, and made it worth 12 marks without all these sub-steps. Again, nowadays they tend to break it up. They scaffold it. It's the words we use, and they break it up into sub-questions. Okay, so we are looking for the coordinates of the point where this graph has a local maximum. They have kind of given away the trick here because they haven't said points. Now we know that a cubic function tends to have a quadratic first derivative, and as a result, we are expecting to get 2 turning points or 2 local values. This one only seems to have, or possibly only has 1. Let's have a look. Okay, but they are talking about a single point, so maybe we need to think about what they mean here, because I haven't said points, and that for me is a bit of a flag. Okay, so 10.2. To find a local maximum, we are going to make the first derivative equal 0. So we're going to say, therefore, f dash equals 12 minus 3x squared equals 0. We can simplify this down to x squared minus 4 equals 0. So x equals 2 or x equals minus 2. Again, please be aware that because we're dealing with a quadratic function, we are in fact looking for 2 values. But again, they want us to do some thinking. And the thinking they'd like us to do here is that because this function is a negative x cubed, it will have a shape that does something like that. And so the local maximum will be the second of these 2 values. So the local maximum will be the bigger value. So this here is the x value of the maximum, and this here would be the x value of the minimum. So they ask us to find the coordinates. So again, having found the x value, how do we find a coordinate? How do we find a y value? We sub it in. So f of 2 equals 24 minus 8 equals 16. So the coordinates here will be 2 and 16. Okay, again, a thinking question. The doing was not all that difficult, but there needed to be some thinking that went with our doing here. 10.2.1, looking at the second one here, calculate the x and y intercepts. Well, 10.2.1, we can see that if you made x equal to 0, f of 0 would equal 0 minus 0 equals 0. So we know that it goes through the origin. Okay? Again, having read ahead, because this is what we do, we know they're going to be asking us to sketch the function just now. So we may as well start putting the values in as we are working, because it helps us with our thinking. Okay, so we know that this function is going to go have a turning point, a local maximum, over here at 2 and 16. Okay, so over there at 2 and 16. We know it is going to have a minimum over here at minus 2, but we need to just keep track of that because that's not actually an x cut. We know that it goes through the origin, but we know also that this function is going to have this shape, as you said here on the left here, that's going to have a shape that does that. So we know that we need to be careful here. So let's have a look. Okay, so let's have a look at what's going to happen. We need to find our other x cut, okay, or cuts. And in this case, we're going to say, cool, y equals 0 to find x cut. So 0 equals x times 12 minus x squared. So again, we're going to get x equals 0, or x equals the square root of 12, or x equals minus the square root of 12. Remembering that the square root of 12 will be 3 comma something. Let's go about 3.6. Let's have a quick look on the calculator. Square root of 12 equals 3.46. So 3.46. I would leave it as the square root of 12 on my diagram. Okay, so I know that this graph is going to cut here at I know it's going to cut here at 0, at root 12, and at negative root 12. And I know that because of this function having the shape that it is, because it's a negative cubic, that it will have this sort of shape. It will be coming in from the top left. Okay, it's got to turn and get through 0. it's got to turn at 2 and 16 and come through 12 and exit. Okay. However, I know that it is going to have a turning point here because of what we had earlier. We know that this other turning point is going to be at -2. We need to find out its value. So again, let's have a look at f of -2. And what we got here is -24 plus 8, which in this case equals -16. Now, it is not totally surprising to me that this graph has a certain element of symmetry about it, but that comes from experience, and hopefully you guys will gain that experience prior to final exams by doing as many exam pass papers as possible. What is missing from this is our point of inflection, and I'd like to look at this from a different perspective. Now, please note that what I'm about to say only works for cubics. Okay, it does not work for other functions, it only works for cubics. But the point of inflection is going to be the midpoint of your turning points. So if I've got the turning point 2 and 16, and my other point of -2 and -16, then I know that the point of inflection will be this thing's midpoint. What's halfway between 2 and -2? 0. What's halfway between 16 and -16? 0. So believe it or not, this point of inflection is also at the origin. To prove that this is true, I'm going to do it the standard way, which is to take the second derivative. Second derivative here would be equal to, where's our first derivative? Our first derivative was -3x squared, so it's going to be -6x. We make that equal to 0, and as a result, x equals 0, and we already knew that f of 0, our y value, would be 0. So our point of inflection would be at 0, 0. Now, what is kind of nice about having two different ways to do something is it does mean we can confirm that our work is correct or not. Okay, thanks very much for today's lesson. I hope you have fun practicing your curve sketching. All the best going forward.